Sounds impressive. Good luck.
Is this signal on? Yeah, it seems to be on. Perfect. So hi, my real name is Guillaume, but I've long given up on getting English speakers to pronounce it, so Bill is just fine. I'm a postdoctoral researcher at École Polytechnique Fédérale de Lausanne in Switzerland. And if you want to follow along with these slides, which I hope are displaying perfect, you can just check out this link, gdal.github.io/JuliaCon 2024-HMM. So a little bit about me. You might have seen me wander around on Discourse or GitHub. My handle there is gdal. I'm interested, broadly speaking, in machine learning and discrete optimization, which is why I was trapped into maintaining the Julia Graphs ecosystem and the Julia Diff ecosystem as well. And especially going to advertise for my second talk, which is called Gradients for Everyone, a quick guide to autodiff in Julia, because I feel like many people don't really know how autodiff works or how it can be useful for them. So if you're interested in that, come see me and Adrian Hill tomorrow at 2:30, I think. So without further ado, what is a hidden Markov model? If you know what a time series is, great. If not, it's just a series of measurements at regular time intervals. So you can think of, I don't know, the temperature at a given point of the Earth, or the number of people crossing a pedestrian street walk, or something like that. Anything that is a temporal process, you can model with time series. And a hidden Markov model is one of the simplest ways to put a statistical formulation on a time series. It splits this into two parts. There's the notion of hidden states, which evolves through time, but which you cannot observe. And then you have observations y that are dependent on the state. So it's basically a noisy Markov chain. The x being the Markov chain and the y being the Markov chain plus the noise, or going through some noise. The way I used this in my PhD thesis was to model train degradation. I was working with the French railway company SNCF, and the idea was that the trains in the fleet give off lots of measurements every day on how they're working. But they don't tell me exactly straight up, okay, I'm feeling a little bit bad, bring me to the garage so that I can get sorted out. This is a hidden information. This is a latent health state of the train, which is slowly deteriorating through time. And what you observe is not exactly this state, it's whatever the train is doing at that point. So it may send me a message saying, okay, my door was opened, or my motor got started, or I got stuck on the track. And so this is indirect information that still gives you some notion of what the health state might be, but it's not exactly the state. So that's why it's a hidden Markov model, where you need to somehow go back from the observations to the state. And just as an example, I like to think of it as basically Grandpa's large language model, because the very first Markov chain was actually suggested to analyze text from Eugene Onegin. So this is a paper by Markov himself, who was basically interested in modeling language through transition probabilities between letters or between phonemes. So one of the first applications of hidden Markov models was in speech processing, but there are plenty more, especially in bioinformatics, where it's very useful to represent DNA strands or proteins, where you have parts that are coding or non-coding, and this is not always obvious at first sight. And as I said, it can be used in predictive maintenance. So let's talk a little bit about the math. This is the scary part, and then we'll get to the fun part where I talk about Julia. So in a typical discrete time, discrete space, discrete observations Markov model, hidden Markov model, you have n different states, and in each of those states you can give rise to m different observations. And the three main parameters that you're going to be interested in are, first of all, the initial probabilities. So when the Markov chain starts, your initial state can be in any one of these configurations with a certain probabilities pi. Then you have the transition matrix. If you're in a given state I at time t-1, you have a certain probability of jumping to the next state j at time t. And this is stored in the matrix A. And finally, you need to represent how your observations are generated. And here, in the simplest of cases, you can represent it as another matrix B, which tells you that when I'm in state I have a certain probability of emitting observation k. And remember, I and j live in the same space here. They're the state space, but I and k don't live in the same space. Like, one is a state, the other one is an observation. It just happens that they're both discrete, but that's just for ease of exposition. So let's make an example. I did some big data handling on the past JuliaCon conferences. So as far as I've been able to reach into the past, there have been 11 editions, many of them happening in the States, 3 happening online, and 2 happening in Europe. And I've analyzed this big data set to find out what the transitions were historically between the various locations at which JuliaCon occurred. So, for instance, there was one transition back at the end of COVID where JuliaCon went from being online to happening at MIT in Boston, and another one which we're living this year where it transitioned from being in the US to being in Europe, which means I could attend. So this would be a state space. But imagine you're not very tuned into the Julia community. For instance, you're my mom. And the only thing my mom knows is whether I'm attending or missing the conference. She doesn't know where it takes place, but she sees me come and go and thinks, okay, he's going to the conference or he's missing it this year. So this would be the observation, whether I'm attending JuliaCon or whether I'm missing it. But imagine she doesn't know where it happens, and she wants to sort of figure it out based on the observations. And again, some big data going on here. Every time JuliaCon was online, I attended. Every time JuliaCon was overseas, I didn't because I don't fly for conferences. And when it was in Europe, one time I was too young to attend, and the other time is today. So this is our data set. Now, how do we represent this as a hidden Markov model? Well, first we need to handle the states. So the initial state probabilities, if we say that this is online, this is overseas, and this is Europe, we have 0, 0, and 1 because there was only one first JuliaCon, so our historical data set is rather limited. Then we have the transition matrix. So assuming I'm in a row here, the first row represents transitions from an online JuliaCon to somewhere else. And there have been 2 transitions from online to online, and there has been 1 transition from online to overseas. This is reflected here in the coefficients. Out of all the transitions that I observed, assuming this is the true model that I observed, we have 2/3 of a chance to remain online and 1/3 of a chance to go overseas. So this is how you would build a hidden Markov model, assuming that what we observed is the true data and it faithfully represents the model. And here, similarly, we have an emissions matrix where if I'm in the state online, the probability is 1 for me to attend. If I'm on the state JuliaCon being overseas, I will never attend. And if it's in Europe, well, it depends how far I am and whether I'm busy at the moment, but I'll try to make it because I can make it by train. So these are our parameters. Now, assuming you have parameters like these, the questions that you can ask if you're my mom, and if you know a little bit more statistics than my mom, is one of 3 questions. The first one being the observation likelihood. You want to estimate, given a sequence of observations, y from time 1 to time t, what is the likelihood that I would observe this sequence of observation? And this is especially useful for estimating parameters later on. So this is one question that you might want to ask, and the answer is given by the forward algorithm. Then you may want to ask, okay, I have observed this sequence y. What is the most likely sequence of states that could explain such observations? And that is solved in turn by the Viterbi algorithm. And finally, you can ask, okay, I have 1 or more observation sequences, but this time I don't know the model. So I want to estimate the parameters P, A, and B based on the observations that I have at my disposal. And this in turn is solved by the Baum-Welsch algorithm, which is a variant of expectation maximization, if it rings a bell to you. So you can see this amazing tutorial from 1989 for details. Here I'm mostly going to focus on what it looks like in practice and how you can use it for your own applications. So let's talk about how I implemented these in Julia, and then we'll talk about why I implemented these in Julia. So my package is called hiddenmarkovmodels.jl. You can find it on GitHub. It's registered. You can just install it very easily. Here I'm demonstrating how it works using observations that are generated by distributions.jl. So here you're going to recognize my faithful JuliaCon attendance dataset, where I just reproduced the initial vector of probabilities, the transition matrix between states, and the emissions matrix, which links states to observations. There's a slight tweak here because from this emissions matrix, what my model actually eats as an input is a vector of distributions. So it's not enough to give it probabilities. I have to turn each row of the matrix B into a categorical distribution telling me that when I'm in this specific state, I have this and that probability to attend or not attend. So initialization, transition matrix, observation distributions, that's all you need to build a hidden Markov model. From there, a bit like the maximum entropy graphs from earlier, you can simulate them. So if I'm asking my model, okay, simulate me a new sequence given your parameters of length 5, then it's going to give me 2 objects. It's going to give me a state sequence, which normally you don't observe, right? But in simulation, I can do whatever the hell I want. And it's going to give me an observation sequence. And here you're going to see, for instance, that it always starts with 3 because the initial probability of starting with state 3 is 1. Now, this is the real data of attendance. So the state sequence, it goes US, 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 London, US, COVID, 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 US, Eindhoven. And the observation is I've missed all of these JuliaCons because I was a baby, and then because it was online I attended, and then I missed it because it was in Boston, and now I'm here before you. Now you can ask, what's the log likelihood of this happening? And the answer is given by this function, log density of the model applied to the observation sequence. So that's the first challenge. Check. Now you could ask, given this observation sequence, what's the state sequence that would explain it best? Because it's not necessarily the true state sequence. And indeed, when you apply the Viterbi algorithm, you get another state sequence, which is slightly different, but which happens to have a higher log density. It's actually lower on this one. So pretend I didn't say anything, pretend you never saw this. It should be higher. So I'll investigate what's going on. I had to do these slides late last night because I switched with our keynote speaker. So theoretically, I should have had more time to procrastinate. Now, the most important part is what happens when you don't know the parameters of your model. So here we're going to imagine we have a slightly longer sequence. We're going to learn from a sequence of a length 1,000 time steps. And we're going to initialize a model with random parameters, except we're giving it the same distribution. So that's actually a nice thing about hidden Markov models is sometimes you can say, okay, I'm pretty sure that these distributions are the correct ones. I just need to estimate the state parameters or vice versa. So here, that's what I'm doing. I'm using a random probability vector for my initial probabilities, a random transition matrix for my transition matrix, and then I'm building my initial model that way. Because the Baumwelsch or EM algorithm is a local optimization algorithm, so you need to give it a starting point. You can't just say, okay, work from nothing. You got to give it a place to start. And when you give it a place to start, and when you apply this Baumwelsch algorithm to our long observation sequence, what you find is a transition matrix that very much looks like the one I gave as input. So we have these 2/3 of probabilities from going from online to online. This 1/3 here, this is the probability of overseas. And what's interesting is it's not exactly the right probabilities, right? But as you feed in more and more data, it will converge to the right probabilities, assuming your initialization was well chosen. And as you can see here, one interesting property of the Baumwelsch algorithm is that the log likelihood is strictly increasing. So this is a nice convergence and debugging check for your models. If your log likelihood is decreasing somewhere, you screwed up. Now, this is the Julia advertising part, but not just Julia advertising, really justifying why we needed a new package in the first place. Because there were lots of alternatives in the Python ecosystem. First one being based on NumPy, this one is based on PyTorch, the last one is more recent and based on JAX. And in Julia, we had one package called HMM-base that was based on distributions.jl. And so when I came up with this problem for my work with the French railway company, as I told you, what I was working with was a very specific kind of distribution because it did not output just a number. It was not just a normal distribution. My observations every day were sequences of messages sent by trains at very specific time steps. So in technical terms, that's called a temporal marked point process. And that's a bit more complicated than what you can model with distributions.jl. All you can do with distributions.jl is output scalars or vectors. And anything more complicated than that, well, you need to roll up your sleeves and do it yourself. So I did. And for every part of HMM-base, which was, by the way, an amazing inspiration for me, I asked, how can we make it more generic or faster or reliable? So let's see how I did it. First part was number types. There's a frequent notion in the Julia community, especially among beginners, that everything needs to be float 64 all the time. And half of the questions you see on discourse are related to this. They need float 64 everywhere, or they get really stressed out. But it turns out that what you need is not a float 64, or not even a float. What you need is something that acts like a number. In particular, something that you can add, multiply, exponentiate, etc. But that's true of numbers more broad and generic than float 64. And what this gives you is, for instance, the ability to apply your code with varying levels of precision, single precision, double precision, arbitrary precision. You can do automatic differentiation, as shown here with forward diff. So if you have An HMM whose parameter mu is the input of a certain function, and you want to compute the log density of this HMM on a fixed observation sequence here. So it's not the same HMM as before, right? It's an HMM with a fixed random transition and emissions and normal distributions. And assume you're not sure which parameter mu is the best parameter. You probably want to estimate it using some kind of gradient descent, maybe, as an alternative to Baum-Welsh. Well, you can do that if your code is generic enough to support forward diff. And that means not forcing everything to be float 64, but instead leaving the door open to more generic number types. Of course, with this comes a bit of a challenge, that is using parametric types everywhere and handling promotion correctly, because you're going to mix several different number types in your algorithms. The transition matrix might have elements that have a different type than the emissions matrix, or that the initial distribution, or that the observations. And so you need to find out what is the correct promoted number type that can handle everything you throw at it. Same reasoning goes with matrix types. In HMM base, the transition matrix was coded as a dense, standard built-in matrix, but really there's no reason to do that. And in particular, for very large-scale hidden Markov models, you often don't have every possible transition. For the same reason that any large-scale graph is sparse, any large-scale hidden Markov model is sparse, because you can't just go from any state to any other state. And so in this case, what I show on the left is that you can build an HMM with a sparse matrix, and when you apply this local optimization algorithm that estimates the parameters, you end up with something that's also sparse in the end. So the sparsity pattern is preserved by the Baum-Welsh algorithm, which is another very nice property. The benefits of that is that it allows you to scale to much larger state spaces and handle realistic transition structures. But of course, it becomes a bit tricky when you have to handle basically abstract matrices during parameter estimation. Now, as I told you, my main motivation for this was to go beyond distributions.jl. And what you need to realize to do this is that you don't really need all of the fuss that comes with distributions.jl. The only two things that you need to build an HMM with a certain observation distribution is, one, a way to sample it, so draw random samples from it, and two, a way to compute log likelihoods. And if you have these two things, then it doesn't matter if it's a distributions.jl or something from measuretheory.jl or a point process, you're good to go. So here I give you an example. I define a custom struct that's called mydist, which just has a length. And here I'm only doing the sampling part. I'm going to say, okay, as soon as I sampled something from a mydist object, you're just going to give me a random string of the given length. And using that, you can build an HMM with this custom distribution types. Here you see that there's one mydist object per state, and they're parameterized by an integer going from 1 to 3. So there's 3 states and 3 observation distributions. And when you sample from it, it goes exactly as you would expect, except that your observation sequence is no longer numbers or arrays, it's strings of various lengths. So just by leveraging the fact that I can use rand, because, well, this is the commonly agreed upon way to sample for something, I can build HMMs that are very, very, very more generic than distributions.jl. But of course, this raises the question, what is the correct interface to specify something that acts like a distribution? And this is a frequent problem in the Julia ecosystem. The notion of interface is not well defined. Now, I've already mentioned automatic differentiation with forward diff. If you're a bit well versed in this domain, you know that you can use other types of automatic differentiation like reverse mode with zygote. And to do that, it's actually a bit tricky because it doesn't handle code that has mutations in it. As soon as you want to access and modify something inside an array, zygote will roll up on the floor and cry. So what you need to do here is you need to write some custom differentiation rules that bypass the mutations in your code and that tell zygote how to proceed in this case. And the benefit that you get is that for large-scale parametric systems, gradients in reverse mode are much more efficient. But no spoilers, you'll get more information about that in our AutoDiff talk with Adrian. And finally, in my application case with the French railway company, we also had a layer of controls because the trains were not in an isolated environment. The trains were submitted to more or less intense activities. For instance, they might travel more or less distance in a given day, they might make a given number of stops, and all that puts different levels of pressure on our system. If you travel more kilometers, if you stop at more stations, then you're going to age quicker and your degradation will happen faster. So it's not just a hidden Markov model, it's a hidden Markov model where the state evolution and the observations are influenced by exogenous variables or controls. And again, this is enabled by interfaces that I baked into the package so that this kind of temporal heterogeneity can be modeled, so that you can have a system whose evolution is not constant through time but depends on whatever external action is thrust upon it. But of course, it makes the estimation methods a bit more complicated. So here is an example where I define a structure that is essentially a Dirac distribution, so it just always returns the same value. And then I define a struct that is a Dirac HMM. And what it's going to do is it's going to have a certain number of states. The initialization and transition matrices are going to be very simple, just uniform probabilities everywhere, 1 over n. And the observation distributions, given a control variable here, it's just going to be the Dirac of that control. So it's a stupid HMM, right? You give it a control variable, it's going to output a control variable. But it's just a 3-liner to show you that all you need to do to handle these control layers is redefine 3 functions. The 3 functions that make up your model: initialization, transition matrix, observation distributions. And this is what I call the abstract HMM interface. And once you do that, you can do whatever you want with your HMM, custom controls, custom estimation procedures, etc. Now, of course, what we all want is more speed. So I added some type stability checks that are tested with JET for all the major subroutines. And this is essential because when you want custom types, you also want to generate efficient lower level code for them. I made sure that none of the central subroutines allocated any memory at all. So everything happens in place if you want it to. And I extended this capability to multiple sequences because when HMMs are involved, handling multiple sequences is embarrassingly parallel, so you can just multi-thread it and you get an instant speedup that is almost equivalent to the number of sequences. Now, finally, I tried to do a package that is a bit more reliable than the Python and Julia counterparts, using unit tests, of course, but also writing documentation and tutorials with literate.jl, which I heavily recommend for translating Julia files into Documenter web pages. And I ran benchmarks against every competitor out there. So the Julia competitor and the 3 Python ones. Ours are the blue ones with the stars because we are the stars in this domain. And as you can see, we're basically faster on every one of the main algorithms, except for this one, where Dynamax does better than us and JAX. Now, I want to briefly conclude by highlighting the role of interfaces. And I have another talk about this, but really I want to get you to think about what it means to define an interface. I rely heavily on those in the package. I rely on the number interface because I manipulate numbers without imposing that they should be float 64. I rely on abstract arrays for transition matrices. For observation distributions, I took my function log density from somewhere, and that somewhere is called density interface. And I define myself an abstract HMM interface with a handful of functions that can handle everything from random simulations to learning. And a bit of a caveat here, the Julia tradition is to say the doc is the API, that the API is defined in natural language on the doc web page, and most of the time that is not enough to do exactly what you want to do and ensure that your users implement this correctly. So whenever you write a package that has an interface, ask yourself, how can I make it easier for my users to avoid getting things wrong? And finally, I also invite you to publish the software that you write because packages are valuable research contributions. They should be put on an equal standing with more theoretical research papers, and that's why they need to be cited and recognized. So if you write a package that you think has a good chance of being used by somebody else, think of the Journal of Open Source Software. It's a very pleasant and open review process on GitHub. Reviewers are always very nice and they really try to improve your work. It's not like a machine learning conference where they just try to destroy your work. Their goal is to sort of work with you to improve the package, to give it, to bring it to a point where it can be published and recognized in the scientific community. So it actually makes me happy to review for JOS, which is sufficiently rare in the academic world to be mentioned. That's it for me, and if you have questions, I'll be happy to take them, or otherwise just reach out on Twitter, GitHub, Slack, Discourse, really carrier pigeons, anything. Thank you for your attention.
So thank you, Bill. I think you've timed this presentation excellently. There are 5 minutes for questions. Who has a question? Okay, I'll just go for the first guy.
Thank you so much for the talk. For those algorithms, map estimation, etc., you had many options to pick those inference algorithms. Why did you pick those 3?
Actually, I don't have many options. So for generic probabilistic graphical models, you have many options because the estimation algorithms are not closed form and they're not polynomial. So you have options between approximate algorithms like MCMC or variational inference. For hidden Markov models, it just so happens that the structure of the model is a tree, and that means that every estimation or inference algorithm is actually polynomial. And so there's one way to do it. There's one good way, and it's that way. So in simplest cases, that is basically all you want. When you go to very large state spaces or fancy situations, you might want something else, but for, let's say, 99% of cases, there's one right way, and this is the one that everyone has in their package.
Another question, the question of interface caught my attention. I was curious about your take in order to enforce a kind of a more formal or obvious and reliable interface.
I experimented with several solutions for defining interfaces. I ended up using none in this package, so I'm a bit of a fake advertiser, but I'm giving a talk tomorrow on one of these solutions, which is interfaces.jl. And there's another one called requiredinterfaces.jl. There's yet another one called ducktyping.jl, which popped up recently. And all of these third-party packages are trying to answer the question, how do we define an interface and how do we test it? And in interfaces.jl, the answer is basically, you can't really define an interface, but you can provide functions to test that if a user implements something, it does what you think it should be doing. So the approach that we're presenting tomorrow with Raphael is basically an interface is a set of tests for said interface.
Thanks so much for the talk. It was great. This is probably a more general question because I'm very new to all of this. But when you're talking about the interfaces you used and the interfaces you found online, do you have a way of kind of thinking, okay, I've got this package I need to write. Has someone already written it? Where would I find the right package or the right interface online amidst all of these, 250,000 packages or something like that? Do you have a way of going about finding the right package for your work?
So, as you'll notice, even my benchmark of the ecosystem is very partial because I didn't mention R. And the reason is very simple. I can't code in R, so I wouldn't have been able to benchmark it anyway. I have no doubt that there are epic packages in R for HMMs. So I searched the 2 languages I knew how to compare, Python and Julia. For Julia specifically, 99.9% of packages are on GitHub. So the first thing you should do is look either on GitHub or JuliaHub for the keywords to your package. And that's incidentally also why I advocate for explicit package names. Please don't name your packages with acronyms or shortcuts, because you may not know what an HMM is, but you might find it if you look for Hidden Markov Model. So while the acronym may seem standard in statistics, it's not in general. So yeah, the first place to go is GitHub, and then I try to keep updated on what happens in the community by following the discourse posts. Package announcements usually end up there. And then once you find whatever's state of the art in the ecosystem, it becomes a question of, do you want to contribute to it, or build something new? And in that case, I reached out to the developer of HMM Base, Maxime Mouchet, and chatted with him about why he did it the way he did and what could be improved in his package. And I tried to learn all the lessons from what he did well and improve what he didn't do well enough. And at the end, he agreed to designate Hidden Markov Models.jl as sort of the successor official package of his own. So I think the biggest question is not how to find what's already there. It's more like what you do once you find them. Is it really justified to start from scratch? Or can you improve what's already there, and even if it means spending more time and frustration in pull requests that never land or things like that? So that's not a solved problem because we're missing manpower in Julia in the whole ecosystem. But yeah, for this one, I chose to start everything from scratch. In other cases, like the graphs ecosystem that I'm maintaining, obviously we're not gonna start from scratch. So we're trying to fix the bugs and pull out fires.
So it's time. Thank you. Great questions. Maybe a round of applause.